Ladies and gentlemen, it's the last day of the show. I hope you're not tired yet now, but we have another SiC session today, as it was too much to bring it all into one yesterday. So we will instant start with Ranbir, and it's his turn now.
Good afternoon. Welcome. My name is Ranbir Singh. I'm president of GeneSiC Semiconductor. The title of my presentation here is Superior Figure of Merit, Silicon Carbide Mosfets from GeneSiC. So to give you an idea, GeneSiC has a pretty broad offering of silicon carbide power MOSFETs, ranging all the way from 750 volts, 1200 volts, 1700 volts, 3300 volts, and 6500 volts. The 650 volt products are yet to be released sometime later this year. I do want to mention to you that many of these products are offered in bare die format and also in package format. We have made some of the largest devices, highest power devices made in silicon carbide ever. For example, our 6500 volt 50 milliohm and 3300 volt 15 milliohms are one of the largest, highest performing devices reported in the industry. So we have over 50 plus products in the relevant milliohm classes. So why, how should you look at a silicon carbide MOSFET? You know, there are many characteristics that basically, if you look at a 1200 volt 75 milliohm MOSFET from various suppliers, they don't work the same. There are many aspects of it. So for example, what are the figure of merit? So we can claim to have 20% better figure of merit than the next best performance metric, this kind of performance metric, which is R on QG. And actually not just we, but if you look at the latest System Plus report, they have also mentioned the same thing. So it leads to high efficient cooler operations, so basically lower RDS on versus temperature. Robustness is basically high avalanche ruggedness and also short circuit withstand times. So we test all of our devices to avalanche before they are passed for selling, packaged devices, and we have superior short circuit withstand time. Reliability, you should always look for no threshold voltage drift. We have best-in-class threshold voltage stability, and overall a stable performance of the body diode condition. So we have worked hard to make it very reliable and robust body diode. Quality in terms of a robust manufacturing process, both from a design standpoint and from the manufacturing standpoint. We have an automotive qualified line that we use to make our devices. It's a fully Class 10 CMOS line with 15 years of IATF automotive standards. And of course, finally, you know, the customers have to consider what the price of the product is and how quickly you can turn these around for your customers. And certainly we do offer a superior price performance index and a high volume capacity of silicon carbide with low lead times. Okay, this is a little bit of a busy slide, but kind of captures the comparison of real measurements that we have done on our Gen 3 silicon carbide MOSFETs as compared to a trench device and also a planar device. If you look at the top two curves here, 2 points here, they mention cost performance index, essentially an RDS on specific comparison. We come out ahead even as compared to some of the trench suppliers out there. Actually, all the trench suppliers out there. In terms of RDS on at high temperature, lower is better, and certainly we offer very low RDS on versus temperature. There are various aspects which determine the switching speed and switching losses. For instance, internal gate resistance, gate charge, output capacitance, and millicapacitance. And while we have extremely low internal gate resistance on our devices, the other aspects, we are comparable. With some we are over, some we are under. And in terms of ruggedness of these devices, we offer some of the best short circuit withstand times and avalanche energies for our silicon carbide MOSFETs. So now I want to talk about the future. GeneSiC is presently, fielding its Gen 3 technology, which is already offering the best figure of merit as compared to any other supplier. But we are moving to a 4th generation device. Some of the alpha samples are already available. What is the difference between these two technologies? So, for example, what we are showing you here is the GeneSiC Gen 3 device, which is in this gold color, and in this purple color, which is the next best device we could find. If you look at the Aron specific, it's right around this number. But if you look at high temperature, it goes up quite a bit for our competitors, but it goes up much less for our devices. So, for example, for automotive traction applications, we have a present device, which is a 5 millimeter by 5 millimeter, moving to a Gen 4, which would be a 4.45 millimeter by 4.45 millimeter, which has finally at high temperatures, the G4 technology will offer 15 milliohm as compared to a competitor's 14.8 milliohms, while still having very low RDS on at room temperature. Why is this important, even though this seems like a higher tempco? Because for a bigger range of this temperature range, we offer very low losses, and that is important for the low resistance at most of the temperatures is where a traction motor spends most of its time. So if you overall calculate the efficiency, you get a much better efficiency. I thought I had another slide, but thank you very much for your attention.
Thank you, Ranbir. Jan, it's your turn now. If there is no question, Jan will start.
Thank you, Bodo. Hello, everybody. My name is Huijink. I work for WeEn Semiconductors, and I'm the technical marketing manager in that company. So, first of all, I would like to introduce our company, because not everybody knows where we are coming from. We're a new company, but also we have a long legacy in power electronics, because we are a former product line of NXP. In those days, we were the bipolar power product line, so high voltage products. In 2015, we became WeEn Semiconductors, and that is also the year that we started to do silicon carbide diodes, at the time 650 volts. Later, we also introduced 1200 volt parts. We started to do automotive silicon carbide diodes, and last year we introduced generation 6 silicon carbide diodes that are actually low VF types. So a low VF means that you not only have the very fast switching performance, but also you have low VF and thus lower conduction losses. And very important, last year we introduced our first silicon carbide Mosfets at 1200 volts. So about our diodes, as I said, we have 650 and 1200 volt silicon carbide diodes. They're made in MPS technology, and we use wafer thinning when the product is ready. So we take away more than half of the material from the wafer to have better thermal performance. Our diodes come in quite a big range of 1 to 40 amps at 650 volts and 2 to 50 amps at 1200 volts. So we also have silicon carbide diodes in the very small packages like SMB. Then we have singles, doubles, etc. Okay, our Mosfets, we introduced them last year. We have now 3 parts released. All of them are 1200 volts in 4-pin TO247 and 3-pin TO247. And we are very happy how they came out. We have a high threshold voltage of 3.5 volts at 25 degrees. So it means that if the threshold voltage is high, you have a lower chance of a spurious unwanted turn on if you have ringing on the gate. The VGS ringing is very limited. This is good for gate oxide reliability and EMI. Low thermal resistance, Blocking voltage is very high, so for nominal 1200 volt parts we see blocking of around 1600 volt in real. And we have a very good figure of merit. Figure of merit is the multiplication of gate charge and RDS on. So you want low gate charge for fast switching, you want low RDS on for low conduction losses. So if you multiply the two, that's the figure of merit. That should be a low value, and actually that value in our case at high temperature is very good. Applications, yeah, switch mode power supply, uninterruptible power supply. Of course, EV chargers, onboard chargers, motor control, energy storage systems, etc. So here is the TO247 4-pin package. So this package has an additional lead, which is the Kelvin source. So that's a thin bond wire internally that goes to the control. If you use the 4-pin package, you have better switching performance, lower ringing on the gate voltage, and therefore better EMI, better switching. You could probably go to higher frequency and a lower chance of exceeding the maximum value for the gate voltage, which, by the way, for our parts is -10 is the maximum value on the negative side, and +25 on the positive side. So both for switching and conduction, we're happy with the performance. And applications should be uninterruptible power supply, PV inverters, EV chargers. When we have more automotive qualified parts, also the onboard charger, where the AEC-Q 101 qualification is mandatory. And electrical vehicles for traction. Okay, then our silicon carbide in the near future. This is my last slide. So basically, we are enhancing our diode portfolio with many more products, from low power to high power, small packages, big packages, more parts with low VF. So the generation 6, we want to do more parts, low Q parts, and we're going to enhance our automotive qualified portfolio for diodes. Then for silicon carbide MOSFETs, we, in the course of this year, will introduce lower RDS-on parts, 20, 30, 40, and 60 milliohms at 1200 volts. This should be ready before the end of this year. We're going to do also 650 volt MOSFETs, and 3.3 kilovolt MOSFET is definitely also in our capability, and we're going to build up an automotive portfolio, especially for onboard charger. Another important thing is that WeEn is soon opening its own fully owned module factory. So when we have our own module factory, obviously we can package silicon carbide, but also silicon dies in these modules. And the first packages will be EZ1, EZ2 modules, first for industrial use, and then also for automotive use. And that's my presentation. Thank you very much.
Thank you, John. Let's come up with questions.
Two questions. One is, you produce silicon carbide diode and MOSFET. And the second question, the new generation of diode, you lowered the forward drop, you improved the dynamic characteristics, but about robustness, surge, what is your for the new parts?
Okay, I repeat the question, maybe not everybody heard it. So the first question is, do we produce our own wafers, right? Okay, so at the moment, so it is so our silicon carbide products, both diode and MOSFET, is totally WeEn design. We have our own silicon carbide design team in Shanghai. So it's our design, our product, but for the moment we have to use foundries for the production of the wafer, but definitely within the next 4 to 5 years, I expect that we have our own silicon carbide factory within mainland China. This is very important also to be active in automotive industry. Big automotive customers want you to have your own silicon carbide wafer production. Yeah. Your second question was about robustness, right?
You reduced the forward. You reduced the forward drop, no? In the new generation of SiC, as I understood.
Sorry, I cannot really understand your question.
You reduced the forward drop.
We reduced the
forward
power.
Forward drop.
Sorry? Reducing the forward drop. Reducing forward drop, yes. Yeah. In the diode, yeah. We can make low VF diodes. Okay. Typically, VF for the generation 5 diode is about 1.5 volt. And for generation 6, it is lowered to 1.25 volt. So 0.25 volt lower, which is great because your conduction losses are lower. This we do by making a different Schottky metal. So instead of tungsten, we use a different metal, and then you can make lower VF. However, you pay with a higher leakage current then. So if you do this, the price you pay is higher leakage. And we did benchmark studies, and in fact, our leakage we saw is the leakage increase is very reasonable, and sometimes the leakage increase less than competitor parts with low VF. Okay. So
the question is with the low VF about the surge. Surge is better or is lower?
The charge.
Surge.
Size.
Surge. S-U-R-G-E.
A surge current. A surge current is indeed maybe a bit less than the generation 5. Okay. So it is not so that generation 6 is per definition better than generation 5. Huh? It is horses for courses. So it depends really on the application. Engineers should look at how important is leakage, how important is surge current, how important is the VF and conduction losses, and then you best make the best choice based on the application. But sometimes a generation 5 could perform better than a generation 6. Also depending on switching speed. I mean, the lower the switching speed, the more important is the low VF. The higher the switching speed, maybe VF is less interesting and you want faster switching. So it depends. You need to test and check both families. Okay. Yeah, thank you.
Thank you. And we turn over to the next presenter, Francois.
So, good afternoon, ladies and gentlemen. My name is Francois Perraud. I'm responsible for the silicon carbide and multi-chip discrete product line in Littelfuse. And I will today briefly explain to you what offer we have in SiC and also what the business model we are trying to establish. So first of all, our chips. So we have a catalog of diodes and Mosfets. So Mosfets between 900 volt and 1.7 kilovolt. So we are not too much touching the 650 volt area. Between 25 and 750 million, basically. So it's very standard range of MOSFETs. Diodes between 650 volt and 1.7 kilovolts. These are Schottkys, basically. Not only single diodes, not only single MOSFETs, but also half bridges, common cathodes, and a few other simple topologies. And we want to emphasize also our range of packages. So Littelfuse acquired Actins a few years ago. With that came a lot of interesting packages, nice packaging technology, both standard discrete, but also especially, and I want to insist on this today, isolated packages. And specifically, such packages like mini modules is kind of the biggest type of package we have in our discrete range, and we have also this whole series of isolated SMPD and ISO packages, so through-hole and surface mount, where we can basically integrate simple topologies, so like mini modules in a sense. And this is where we want to go with our SiC product family and extending basically, or trying to do a step aside as compared with competitors. We don't want to focus on being seen as a catalog provider of SiC device. So we are trying to develop our family to be a provider of semi-customized multi-chip solution in advanced packaging and focusing on industry. So we are not basically with this product family, not touching automotive at this stage. So how do we do that? So we have, as I said, a great selection of isolated and non-isolated packages. We already have a zoo, basically, of simple topologies that we can put on DCBs. We have, beyond SiC, we have also a huge portfolio of Mosfets and diodes in silicon and IGBT between 150 and 4500 volts, sorry. And we are setting up a rapid prototyping line in our back-end factory in the Philippines. So it's also Littelfuse own factory, so we can package these chips, and thus are in the position to provide our customers with, I would not say customized products, but let's say application optimized product. So just to give you two examples of what we are doing right now. We are developing for a customer a boost leg in ISO plus I4 package with a silicon MOSFET and a silicon carbide diode. So this is an evolution of a full silicon version. So just here the customer desires a bit better performance on the switching of the diodes. We are also developing half bridge leg, full silicon carbide in a SMPD package. So this is once again isolated, topside cooled. It's pick and place compatible, so it's handled with by the same machines basically as your surface mount devices, and provides 2.5 kilovolt AC isolation basically. And we are also developing this right now for an Austrian customer basically who was interested in a slightly higher on version of what we have in the portfolio. Yeah, so that was already all I wanted to show in this very brief presentation, trying to show you the direction of Littelfuse and try maybe to propose a slightly different approach and slightly different business model. Now I'm happy to answer questions if you have any. And
are you able to integrate any other drivers into your multi-chip modules?
It's our next step. I mean, we are first going to look at this kind of simple, I mean, purely power topologies. We are already thinking about integrating drivers for some applications. There is no strong reason why this shouldn't be possible, basically, because as I said, these things are mini modules. So we have and not only drivers, by the way, we can also discuss about integrating NTCs, for example. Current sensors, TBD, depends on the size. Basically, as you see, the real estate is still limited in this package. So we are talking here. These SMPDs are 25 by 20 square millimeters. So obviously, but yeah, we want to push with this idea of integrating a little bit further.
And passives? Capacitors and specific.
Yeah. I see what you mean. Yeah, I don't know. So we need to. It's interesting. I've been talking with a few people here, looking at what might be possible. It surely would be interesting, but it's maybe the next step. Then, yeah.
So good afternoon, everyone. My name is Jorge Mari. I work at Danfoss Silicon Powers. And today I will be showing you a few of the challenges that we have to face when we do multi-chip power modules, in particular, say, high number of chips inside the module. First of all, as a remark about what we have in our portfolio, so there are different ampacities. There are modules for automotive and industrials. So automotive, for example, we have clearly the DCM 1000X. That one is fitted with silicon carbide and also with a shower power on the shower power 3D on the back side of the module. But then we have also in the, say, E3XL type of industrial modules also fitted with many chips in parallel. We also have an interesting module, the E2 that appears over there, which is an full H bridge, 4 switches. So both high side, low side, let's say, on 2 legs at the same time, and then smaller modules as well. So what are the technical challenges in module design? First of all, one of the important things is what surface is really available in the substrate to place the chips. And the example that I'm showing you there, here, I mean, you can see a big part or big space of the substrate that actually has to be left, say, open without being used for chips, because you have, for example, to do the ultrasonic welding of the feet there, and in order to preserve the cleanliness and to make sure that there's no debris, let's say, around it, then there's a big price to pay on as far as, say, substrate space is concerned. So the other thing is, of course, how many chips are reasonable to place there. And typically this comes from customer requirements. They want very low RDS on, but you may want to do that, but then you are cramping a lot of chips in a very small area, and then you are bringing up another number of problems. The other important thing is also to make sure that you have current balancing between the different chips, especially during the transients, during the turn on and the turn off. So here I'm showing you an example of a module which has, I don't know, about 14 chips or more. And what you can see on the picture on the right side is that this is a simulation of the chips, and the problem is that because they have different, say, local commutation loops and also gate loop inductances, then the currents that during a turn on, for example, some of the chips are seeing are higher than the other ones. So it means that some chips are more stressed than other ones. And so the art of module production is to try to avoid that these things happen. So I'm putting that as an example of what you try not to get, let's say. And related to that is also the fact that the difficulty is to measure at chip level when you have so many chips and so many bond wires around that. So that makes the dependence and the reliance on models available all the more important as well. Apart from the electrical challenges that we saw before, we also have a number of technical challenges in the module design. There are thermomechanical challenges. For example, when you do the substrates and when you place the chips there, you have to make sure that the warping of the substrates when you sinter them, for example, on that, is correct. Let's say that is not creating stresses in the substrate that will ultimately lead to cracks. So that's one of the things that has to be taken into account before, let's say, the production. Then the other thing is also the thermal coupling during the actual operation. And so here we also see some example of chips which are placed on the sides almost of that module. And of course, what that brings is that there's a lot of, say, temperature. The temperature fields are extremely high towards the edges. And if you don't control that, then you have things that, for example, can lead to delamination, especially for chips that are close to the edges. Here, what we see on the right-hand side, on the other hand, is some open-loop module pictures with infrared cameras trying to show, say, the good thermal balancing of the chips in actual operation. So this is what you try to strive to, let's say. A particular challenge with silicon carbide, so the things that I told before are equally, say, applicable for silicon and for silicon carbide. But in silicon carbide, we have a number of other things. One of them is short circuit and surge requirements. So here you can see on the left-hand side, essentially a pulse during a short circuit. So this is a short period of time. And you see the temperature rise at each of the layers in the vertical stack of that module, let's say. And you can see that the top layers, the ones that are close to the junction, actually reach much higher temperatures. I can barely read this slide now, but it's about, say, 800 or 900 degrees. And so, and the lower layers, or the layers that are deep inside the substrate, are less affected by that. The other thing is the surge, which was also mentioned before, because, for example, the body diode has a positive temperature coefficient, and it has a large voltage drop. Then, of course, it is typically more stressed during surge events, and also you meet the problem of trying to balance the currents in a surge event when the chips are taking up different voltages. So that's a big concern. And one another important thing that appears in silicon carbide, which you have also probably all heard about, is the gate oxide and the aging aspects of that. So if you look into a module with multiple chips, then, and if you do a simulation, for example, and you look into the gate source voltage of the auxiliary device, the one that is not being switched, so then you get something like that, this one appearing over there. So all those lines, there's a bundle of lines for each of the gate source voltages in the auxiliary device. So the diode, let's say. And what you can see is that during the turn on event of the other side, you see some spikes and some transients there, which can actually go all the way down, say, to -10, -12 volts. Those are short-term transients, about a few 50 nanoseconds or things of this type, but certainly they exceed the typical recommended operation values of the chip suppliers. So one of the things that you have to make sure is that that thing will not cause long-term degradation on the modules. And for example, what we have been doing in order to make sure that that is the case and not to rely simply on chip manufacturing, say, statements, is we build our own stress testers. In this case, what we have done is a multipolar stress tester. So we not only have, say, on and off, so 2 voltages at which to stress the devices, like in the classical high temperature gate switching test, the HTGS, but in this case we have a 4 voltage one, so you can see that in this waveform we go all the way down to -8 volts, then we relax it to -4, then switch on to +19 and then to +15. And we control the amount of time that we have of that gate source at each of the chips seeing a particular voltage or undershoot or overshoot, which is beyond the actual operating range. And so the idea is that we test these things for many months and then see how the gate oxide changes and the properties of that MOSFET. In this case, we are doing that on the TO247 level. So many discretes that have to be tested in order to make sure that the drift is controlled, that the RDS-on resistance is controlled, and also that all the chips essentially age in the same way so that they will not diverge as you look into a module. Here you see other type of things that happen in silicon carbide when you have multiple chips. You have several types of oscillations. The ones on the far left there are actually the milder ones, the ones that we expect, which are, say, system-induced power loop oscillations that have to do with the interplay between the output capacitance of the chip and the inductance in the loop. So obviously, they can be bad if you don't control your system design. But then there are at least 2 other type of oscillations that we see. One is the so-called intra-chip oscillations, or intra-substrate oscillations, which take place due to the bonding structure and the different inductance that each of the chips is, and the interplay with the transconductance of the chip, and the fact that in essence this is working as a feedback system with positive gain, and if you do not get that, say, the real part of the eigenvalues of the system under control, then you can get to this type of oscillation. So that's things that you have to be careful of. And the other thing that you have to be careful of is also the inter-substrate oscillations. So when you have more than one substrate in a big ampacity module, then this problem can not only happen between the chips in the same substrate, but also across the different substrates. And that's also something that one have to tackle early on, and which we actually do also through the help with very detailed simulation models. That was it from my side. Thank you very much for your attention.
Thank you, Jorge. Any questions from the auditorium?
All right. Hello and good afternoon. Welcome to the presentation of the reduction of strain inductance by the module design. Unfortunately, my colleague is sick and I need to hop in spontaneously. My name is Bradel and I'm an assistant manager. I'm working for Fuji Electric in Europe. So, first things first, let us clarify what are the negative effects of the strain inductance. And it is an undesirable and parasitic inductance which negatively affects the switching behavior and the performance of the product. And one of the One of the downsides is that the surge voltage spikes, which occur during the turn on and the reverse recovery, are quite bad for the switching. And the faster the switch is operated during turn on and the turn off, the higher the voltage spike of the module is. And by increasing the voltage spike, the problem is that there's a physical limit, and when we reach it, we will break the module. Another fact is that ringing occurs, and this would lead to EMI problems, and this would affect the periphery of electrical components inside. And last but not least, there's a physical limit of the slew rate, and there's also not so good for driving this module. So let us quickly check why it is so important to reduce the strain inductance of silicon carbide modules. So the silicon carbide MOSFETs are quite fast in switching capabilities, much faster compared to the silicon IGBTs. And due to this fast and hard switching, the switching losses can be decreased tremendously. And the high switching speeds in comparison with a high strain inductance lead to the high surge voltage spikes, which negatively affect the lifetime of the module. And here you can see some graphs for the turn on and turn off. And in the black curves represent the silicon IGBT module, and the red one, the all silicon carbide MOSFETs. And here you can see that the silicon carbide MOSFETs are switching much faster, much harder, and have some slight oscillations, but very low switching losses. And now the question is, how can we reduce the strain inductance inside of the module, so internally? This can be reduced by simply putting or improving the main terminal structure by putting it closely together so that the current flow to the up side, so to the N terminal, and from the P side to the DCB is cancel each other's out. So what you can see is that a simple change of the design will improve the strain inductance value tremendously. And also another interesting fact is that not only it is possible to reduce the internal the strain inductance from the internal structure, but also from the external side. We can apply this technology also for the DC Link Capacitor, which you can see here in the bottom left, where we have the DC Link Capacitor in the backside, and with this laminated structure, where you have also a schematic on the right-hand side with the red bus bar, you can tremendously improve the design. So let me shortly summarize what we did in the past with this change of the structure. We have these really high switching speeds with the silicon carbide MOSFETs, and they can be improved by a factor of 3 or 4 compared to the silicon IGBTs. And by pushing the main terminals closely by to each other, there's this improvement for making the product a better one. And those applies not only for the internal, but also for the external structures, and not only for the current designs, which is on the market for decades, let's say, for the 62 millimeter package, but also can be applied for future new products. Basically, that's it from my side. Sorry for this spontaneous hop in for my colleague. I'm happy to help, but also my colleague, he is not able to speak, but he is still able to read and write, so please feel free to contact him or me right now. Thank you.
Okay, so these questions should come in by email to the colleague, and thank you very much for presenting. And now, last not least, we have Chris.
Okay, hello everyone. My name's Chris White. I'm engineering manager for Hitachi Europe Power Device Division based in the UK and dealing with our power semiconductor modules from Japan. I'd like to introduce today our new 1700 volt full SiC MOSFET module in our NHPD2 package, where by applying a number of different innovations, we've increased the current density in the module by 50%, delivering some quite compelling performance levels. So we've got a few different technologies applied, and all of this is benchmarking against our mass production module, which is a 900 amp, 1700 volt full silicon carbide MOSFET in our NHPD2 package. So this is the new high power density dual, targeting high power applications in a 140 by 190 millimeter package. Benchmarking that technology, we apply three key technologies. So replacing the die attach from solder to copper sintering gives us substantial increases in power cycle and thermal cycle lifetime in the order of maybe 20, 25 times increase. It says 6 here, but new testing is still ongoing because we haven't yet broken it. It also allows us to increase the maximum junction temperature of the device, operating up to 175 degrees, formerly 150 degrees. And it gives us some small improvement in the thermal impedance from chip to heat sink, which also helps. Second, we are increasing the VGS operation. So previously we were recommending a 15 volt operation. If we increase that to 17 volts, we see good impact both on reducing the conduction loss and also reducing the turn-on loss. I'll show you some more on that shortly. And then we've also optimized the internal RG to make this a much higher switching speed device. So the switching transients we've heard about from our other presenters become much, much faster, and we see a roughly 35% reduction in switching losses. All of this together allows us to go from a 900 amp module in the same housing, same footprint, up to 1,350. And this really is rated to railway traction standards, so designed for very harsh operation with very high reliability and very high quality. You'll see a note down here. We have a concept we're sharing at the moment where we could increase this further to 1,800 amps by applying a direct water-cooled pin-fin base plate to the module, allowing us to drastically reduce the thermal impedance and therefore drive substantially more power out of the module. So just to show this is real, we're sampling this product now to key customers. Here's some waveforms for it. So we're benchmarking the previous generation of the product to the new generation of the product. And we can see substantial reductions here in switching losses with an overall reduction of 35, 37% reduction in switching losses. If we look at the on-state loss, so we see at high temperature, 175 degree, we see a modest improvement due to the higher gate source voltage of maybe 8%, but as we're down at more other operating temperatures, down to room temperature, it's maybe as high as 24% improvement rather, in conduction loss. And a few people have mentioned short circuit. We all know silicon carbide presents some challenges with short circuit compared to IGBTs, but we verified a 3 microsecond short circuit robustness for this module to give you some chance of protecting it before it explodes in a short circuit condition. And here are the waveforms to prove that's all real. So if we take this module now and we run converter level simulation on it, we're benchmarking a couple of different modules here. So if we benchmark, these are all in the same module outline. We benchmark our silicon module, 1000 amp, 1.7 kV silicon module. We are running in converter, I haven't put the conditions on here, but a converter level simulation. And the two lines, one is motoring mode, one is rectifying mode, so power flow, both directions. And we are looking at the available output power, the maximum output current, benchmarked against the switching frequency of the converter. We can see that if we say take a 5 kilohertz switching frequency and we go from silicon to the original silicon carbide MOSFET, we can more than double the output current. Going from, this is the previous generation of silicon carbide. If we go to the new silicon carbide, we're more than 60% increase compared to the the previous generation of silicon carbide MOSFET. Hence the 50% increase in the rated current, but actually you get a little bit for free. We'll give you a little bit more. If we were then to apply this direct water cooling due to the reduced thermal impedance, we can increase that a further 30% compared to this, even compared to this new product. And actually, if we compare it to the original MOSFET, it's sort of 2.5 times increase in current. That's all I wanted to share. Happy to take questions. Happy for you to contact me afterwards. Thank you very much for your time.
Thank you, Chris. It's up for questions. If there are no questions, I will thank you to all of you to make it real happen again, to come together and talk and watch and see and share good information. If you want to be up to date every day, keep in mind my publication is monthly and will reach your desk easily. If you are not subscribed yet, it's free. Drop your business card at our booth or just on the table here, and we take them and process them that you get every month the real crucial news in power electronics, focused also to wide bandgap. On a quarterly basis, we do a roundtable virtually on wide bandgap articles in the magazine, and towards the end of the year, we will do a special wide bandgap event. Just keep that in mind, stay tuned, and you will get the details. Thank you very much. Special thanks to the presenter, and special thanks to the auditorium to make it happen this time again. Goodbye and have a safe trip home. That's what I can say now.